All right, good morning, everyone. Our first speaker this morning is Mann from Cornell, who will talk about Anosov-like group actions.
Great. Thanks very much. Thanks for the invitation. It's a real pleasure to be here. My first time in India, and so far so good. I'm very much enjoying the conference and the whole experience. The problem I'm going to talk about, the motivation comes from, I guess, smooth dynamics, actually. Classifying Anosov flows, or more general pseudo-Anosov flows on three manifolds. But since it's probability and geometric group theory week, I'm going to skip sort of right to start with a framework which came, out of a reformulation of this problem, but it's sort of just an abstract setting about discrete group actions on certain spaces. Okay, and I'll make the connection later on. Okay, so what are the spaces? The spaces are what I call bifoliated planes. So bifoliated plane is just, it's a plane. So some plane P, okay, with a pair of transverse foliations, which we allow to have some isolated, particularly nice pronged singularities. So with a pair of transverse, no smoothness here, just C0 foliations. I'll call them F plus and F minus. Possibly with a discrete set or isolated pronged singularities. Okay. So at some points, rather than being a standard picture of two transverse foliations, you might see something that looks more like this. So examples. Of course, you have the trivial plane. The trivial foliations, just the sort of standard horizontal, vertical, and R2 product foliation. This prong allows you to consider the universal cover of a hyperbolic surface, okay, with the kind of invariant singular foliations from a pseudo-Anosov, or like the nicest Nielsen-Thurston representative of a pseudo-Anosov mapping class. Okay, if you don't know what that means, that's fine. But there's also many examples where you have no prongs, but it's very far from trivial, where the leaf space of your foliation, of either or both, are non-Hausdorff. So if I collapse every leaf of a particular foliation to a point, the quotient space is called the leaf space. And these are always one manifolds, but no need for them to be Hausdorff. So a picture of what this might look like, what does this mean? It means you have a sequence of leaves that limits onto multiple leaves, right? So this is like some open interval that limits onto 3 points here. And this can happen easily, in sort of both directions. I could have a family that's transverse to this and limits onto some finite or infinite union of leaves in that direction, and I could replicate this at different scales, right? These things can look incredibly complicated. Okay. The motivating example comes from geodesic flow, or more generally Anosov flows. So if you take an Anosov, or more generally, I won't define this, but there's a generalization, on a compact three manifold, a closed three manifold. So you can think as a concrete example, you take just geodesic flow on the unit tangent bundle of, say, a hyperbolic surface or a surface of negative curvature. Okay. And Anosov flows, if you haven't seen them before, are a family of dynamical systems that exhibits the same kind of qualitative behavior that you see for geodesic flow and negative curvature. There's directions of uniform expansion and contraction at every point. Okay. So this is just set up. There's no plane here yet. Any three-manifold with an Anosov flow, its universal cover, this is a fact, a theorem, is homeomorphic to R3. And these directions of expansion and contraction, if you take the distribution that includes that direction and also the flow direction, that's integrable. And so you get two transverse two-dimensional foliations up here called the weak stable and unstable foliations for the flow. On the unit tangent bundle version, this is just the horocycle foliations that we saw in Yair's talk. So following along my example, so what does this look like if I took the, I can't draw a picture of the universal cover of the unit tangent bundle very well, but I can draw the hyperbolic plane. I'll draw the universal cover of the surface. And the horocycle foliations, right, it's all the tangent vectors, which, so a single leaf of, say, the unstable horocycle foliation is all the tangent vectors that are backward asymptotic to this point. Okay, so one leaf looks like a copy of the hyperbolic plane. Okay. So these are two transverse flow invariant foliations. On my manifold, I can lift them up to the universal covers. So now they're invariant both under a lifted flow and the fundamental group of this. I can lift the flow, and I can quotient to make something called the orbit space. So if I take my universal cover and I collapse orbits to points, so I identify each point x with its whole image under the flow, I get something no longer three-dimensional but two-dimensional. This is a topological plane. Okay. And these two-dimensional foliations descend to one-dimensional foliations. Okay. So I get an example of a bifoliated plane. And this has a nice name. It's called the orbit space of the flow. So it's usually notated O for orbit space phi. If you wonder what this looks like in the geodesic flow in a surface case, there's a very nice picture. It's neither trivial, but it also doesn't have this weird like branching non-Hausdorff property. It looks like, nice way to draw it is you take an infinite diagonal strip, and one of my foliations is now vertical, and the other is horizontal in here. Okay. So this is what I get in the geodesic flow on any surface picture. This is really just something like this. If you've thought about geodesic flow, that's a nice exercise to see why this picture is what you get. And wait, why is this non-trivial? I have horizontal, vertical, right? Well, the property that distinguishes this from the trivial plane is that in the product foliation, every leaf of the yellow meets every leaf of the pink. And here, that's not the case, right? A pink leaf is met by an interval worth of yellow leaves, but not all of them, and somehow there's like a first yellow leaf here that doesn't meet it. And that's going to end up being a sort of an essential geographical feature. Okay, so here's the class of spaces that I want to consider. Maybe I should say, actually, that this is sort of a meta example. Within the class of Anosov flows on 3 manifolds, if you do this orbit space construction, you get, or if I allow for pseudo-Anosov flows, I'll see prongs too. You get crazy examples that have all kinds of branching behavior. You see trivial planes. You see this picture, basically everything. Okay, so that's the space. What's the group action? So here's the next definition. A group, just an abstract G, acting on a bifoliated plane. So when I say acting on a bifoliated plane, I want it to preserve each foliation by foliation preserving homeos. Okay, is called Anosov-like if it satisfies the following list of kind of dynamical properties. Maybe 3 people in this room have heard me talk about this before. This is a simplified version since last I spoke on this. We've been able to kind of improve this definition and show some previous things were redundant. So this definition is becoming nicer, which is good for everyone. Okay, so I want to capture some basic dynamical properties that give me some kind of hyperbolicity. Okay, so the first axiom is that there is some hyperbolicity. So what is this? If I have some non-trivial element in my group that fixes some leaf of either foliation, then the dynamics on this leaf, I'll draw a cartoon. Okay, so here's my leaf L. Okay, then there is a fixed point for G on this leaf. Okay. And of course, there's going to be another, so there's L. I have 2 foliations. All right, so that gives me a second fixed leaf because it goes through this point. And the dynamics on this should be expansive on one and contracting on the other. So you see this dynamical picture. So as I iterate, points of one fixed leaf get attracted towards the point and the other ones get repelled away. So I guess I shouldn't label which one is L because it could be the attracted or repelled, but replace G with G inverse if you like. Okay, so this is sort of the hyperbolicity axiom, or locally, I guess, because I'm really only talking about a couple leaves at a time. The second axiom says that you have some hyperbolicity everywhere. Okay, so we want to require that the union of leaves of each foliation that happen to be fixed by elements, so I see the picture like this, is dense. Okay, so union of the set of leaves so that there is some G, not identity, fixing this, L in F plus. This is dense. And same for the other foliation. Okay, so this says I get this kind of behavior happening everywhere is sort of in the plane. Not that I'll see fixed points everywhere necessarily, but fixed leaves. And the third one says that when you see unusual behavior, you see hyperbolicity there. So prongs are fixed. So for each prong, there exists a group element that fixes the prong point. And also, if I see 2 leaves that are not separated in their leaf space, so for instance, this yellow one and that one yellow one cannot be separated by open sets. That's also sort of a topological pathology. I want to say there's a group element that fixes both. Then exists some non-trivial. I'll forget to write non-trivial starting right about now. So that's always an assumption when it makes sense. There's a group element that fixes both simultaneously. That in their leaf space, you can't put them in distinct open sets, right? They witness the failure of this space to be Hausdorff. Yeah. Okay. That's the definition. Additionally, I say such an Anosov-like group action is transitive. Okay, so this is another thing that you can add. If it satisfies this property, the axiom that I'll call T, okay, which is doesn't seem obvious right away that it has to do with transitivity. But the property is that the set, not just of fixed leaves, but of fixed points is dense. Non-trivial element fixing X. Okay, that's an abstract definition. What are some examples of this to give you a sense? So here's an example, what this looks like. Let's start with the easiest ones. If I take the trivial plane, so just the product foliation, I could take an action of a group of affine transformations. But I need to be a little bit careful. The linear part of these affine transformations needs to preserve this horizontal-vertical foliation. Okay, so it needs to look somehow, everything has to look like a diagonal matrix. And I need to have this kind of expanding contracting behavior at every fixed point. So I either need, lambda less than 1 less than mu, or vice versa. But any group of affine transformations that satisfies this gives you an example, right? So for instance, you could take something generated by one matrix like this and a family of translations, and you would win. Here, I'll give this also as a fun exercise. Which is that this is all that can happen on trivial planes. So if G has an Anosov-like, I didn't tell you what G is any group, action on a trivial plane, then G is up to conjugacy. G is a group of affine transformations, and of course the linear parts have to satisfy this, they have to look like this. Okay. This is an extra, if you know Solidov's theorem, which is about groups acting on the line with at most one fixed point, this is an easy consequence. If you don't, then it becomes a trickier exercise to wrap your head around, but it's worth thinking about. Okay, so let's do some non-trivial examples. Haha. So there's a family of examples on planes that look like this. This picture is called the skew plane. So that's this one. There's a family of examples studied by Thurston that he called extended convergence groups. And what are these? So a convergence group acting on the circle is a group of homeomorphisms of the circle with the property that it acts properly discontinuously on the space of distinct triples. An extended convergence group is not acting on the circle, it's acting on the line, which you can think of as being the edge of this picture. That line is not in the plane, right? That's sort of some boundary at infinity. If you have a group of homeomorphisms of this line, then it tells you where to move all the leaves of the foliation, so you can extend it to a homeomorphism of this bifoliated plane uniquely. And an extended convergence group is one that acts properly discontinuously on a different kind of space of triples. I should write down that this is Thurston in an article called Three Manifolds, Foliations, and Circles. And the types of groups are, so the structure of this plane has a kind of a special feature, which is that each one of these leaves has sort of a first leaf of the other foliation that it does not meet, right? Okay. And that procedure gives you kind of a staircase, right? Which lets me define sort of maybe a parametrization of this line at infinity, where I think of this as being a unit length. So that's x, or that's the origin, this is 1, that's 2, that's 3. Okay. And if I take a parametrization like this, these are groups that act on this line, so that the induced action on the space of unit apart, at most unit apart triples, so distinct triples, so that x is less than y, less than z, less than x plus 1, is properly discontinuous. So if you take, for instance, a convergence group, a Fuchsian group acting on the circle, and you lift it to the line, you will get an example that satisfies this. But there are many more examples than just that. Okay? And the lift of a Fuchsian group acting on the line to this is actually exactly what you see in the geodesic flow example, where your Fuchsian group is the fundamental group of the surface. Okay, so this is a big class of examples. And of course, the sort of meta example. Right. Oh, conveniently, I'm right back over here again. All right. So the key / motivating example. Okay. Is this picture right here. If you have an Anosov flow on a 3-manifold, I can look at its orbit space. Well, first I can look at the universal cover. The fundamental group of your manifold acts on its universal cover, preserving these stable, unstable foliations because they came from lifting something down on your manifold downstairs. Okay. So that works. My flow also was something that was lifted. I guess here I'm sort of abusing notation. The flow is on the manifold, but I can lift it to the universal cover. So this action descends to the orbit space. Get an induced action on this bifoliated plane. And the expansive contraction type behavior for Anosov flows gets promoted to this kind of hyperbolicity for that in the axioms for Anosov-like group actions. Okay, so the key motivating example is the action of fundamental groups of 3 manifolds on their orbit space when phi is pseudo-Anosov or Anosov flow. Okay, and this is not absolutely trivial. I mean, so the way the axioms were formulated to try and capture this behavior, you know, that A3 holds is a theorem of Sergio Fenley in this case. And the T axiom is satisfied if and only if the flow is transitive, hence transitivity. And if you are a dynamicist, it maybe reminds you of an Anosov closing lemma or something like this. Okay. So this is what I want to study, and the motivation, so maybe I'll just say a few words of what we want to do with these. I mean, first, they're an interesting class of dynamical systems in their own right. That's my first pitch here for maybe the geometric group theorists or people who like groups acting on spaces, is that, you know, here's some reasonable dynamical properties of a group acting on spaces as on a big class of spaces. What kind of groups can you see? What kind of other properties do you get for free out of these axioms? I think there's a very interesting theory there. And if you can prove something interesting, then perhaps you've actually proved something about Anosov flows, because this is a big class of examples. Okay, but our motivation was to try and classify Anosov flows on 3 manifolds. I want to keep my axioms up for a second, so let's. Okay, so this problem really comes from Smale's 1966 ICM address, where he outlines a program for classifying sort of a discrete version of Anosov flows, Anosov diffeomorphisms, and at some point says, you know, here's a very important problem. We should try and classify Anosov flows on not 3 manifolds, on all manifolds of any dimension. Maybe just stick to the transitive case because that's easier. So he says that we should do this. We should try and classify, namely find a discrete or a numerical invariance, hopefully complete invariance, Anosov flows. Oh, sorry, transitive. But he doesn't really give a picture of how you might do this, unlike the nice conjectural picture that he has for Anosov diffeomorphisms. And that's because the picture is murky. It's tricky. We don't really know what happens in higher dimension, but on 3 manifolds, there are many, many examples. Okay. That sort of resist a clean classification. This starts with work of Goodman, Sue Goodman, David Fried. Before that, even Handel and Thurston. And many, many, many others that developed sort of technology to take one example, do sort of a surgery construction, produce another one. The state of the art is we have examples of 3 manifolds, even that are topologically not that complicated, that can admit arbitrarily many distinct Anosov flows, up to the natural notion of equivalence where you want to classify these. Okay. But also on 3 manifolds, there's sort of a nice picture, which is this orbit space. So this idea of the orbit space was introduced by Barbeau and Fenley. Independently, they started using this as a tool around 1990, mid-90s, 1995-ish. and are still sort of doing interesting work from this perspective today. They introduced the orbit space as a tool towards developing a structure theory. Okay, so you can kind of reduce, although you have this zoo of examples that are very hard to understand, you can do a trick and reduce dimension by 1, and instead of understanding sort of continuous time dynamical systems on 3-dimensional objects, you have kind of this action of a discrete group on a 2-dimensional object. And one result proved independently by both of them is that the action of this group on this, this group on this orbit space as an action on a bifoliated plane determines the flow up to what's called orbit equivalence. So up to time change and conjugacy by a homeomorphism. Okay. Okay. Okay, so this looked like a promising thing to study, and very recently, with Thomas Barthelm, and then later with Stephen Frankel, and also Sergio Fenley, we used this orbit space tool as a way to find a complete invariant for transitive Anosov flows. That's not complicated for a transitive. In fact, pseudo-Anosov works too. Okay, so let me just state a theorem that tells you that to say that this invariant is not complicated. So here's a one sample theorem of what we do by looking at the orbit space. So this is with Thomas Barthelm in one paper, and then a second paper also with Stephen Frankel. Here's a special case. If you have a manifold that is, I'll do the weakest but easiest to state. If M3 is hyperbolic, okay, then Anosov or pseudo-Anosov flows on this manifold are classified. They're completely determined up to time change and conjugacy by just knowing the set of free homotopy classes of periodic orbits. If you have a, so this is just some very floppy algebraic data. It just records the free homotopy classes every time your flow makes a loop. Write down that free homotopy class. I don't care how many loops represent this class. You just need to know that. If you have a manifold that's not hyperbolic, it has some pi1 injective torus, then for certain of these tori, you need to record a sign. That's the complete invariant that works for all, and it's a little hard to define without getting into the weeds. But the full invariant for, that works for any manifold is just finitely many signs on top of this data. Okay. But what this theorem really is, it comes from this language of translating to the orbit space. So here's a translation. Which is what we actually prove. Here's the theorem. If you have a group that acts on a bifoliated plane. And this is Anosov-like. And transitive. Oops, this should say transitive. Okay. And my simplifying thing to make this easier to state is G has no Z cross Z subgroups. Okay. If so, you should record some signs for certain Z cross Zs. Then this action is completely determined by just some collection of elements of G, just a list. So then this plane with its foliations is determined up to homeomorphism. So you'll know if the plane is foliated or not, is trivial or not, or if it's branching in some way, or if it has prongs or whatever. This is completely determined up to homeomorphism. And the action of G up to conjugacy, okay, by the set of elements that act with fixed points. So by this set, the set of elements of G, so that there exists some point fixed by this. All right, whoops, this kind of got out of hand. Okay, so what does this mean? What do I mean? Determined if you have two actions of the same group and these sets are the same, well, then the planes are homeomorphic, with their foliations are homeomorphic, and that you can find a homeomorphism that conjugates the action. Okay. So this is kind of wild, that just sort of a list of group elements plus these axioms is enough to recover the whole picture. Okay. So this is some advertisement to try and tell you that I think you can get a lot out of studying Anosov-like group actions on planes. And what I want to do for the rest of my talk is just give you a taste of like sort of group-theoretic things that you can, group-theoretic and dynamical things that you could prove out of these axioms. Right? And these will look like actually some ingredients that went towards the proof of this, some that are going towards proofs of other results. Well, let's actually play with this and prove something. Okay, so if you don't like flows, you can now forget about all the flow stuff, and we'll just work with groups acting on planes that satisfy these axioms. Actually, I guess before I totally forget everything, this is an abstract question. I'm very curious about what this subset of G looks like. So suppose you have an Anosov-like group actions, transitive or not, no Z cross Z's or not. Here's some subset of your group that looks interesting. It's big. So you can prove just out of the axioms that this subset has exponential growth, and your group, first your group has exponential growth, and second, this also has exponential growth in word length. But is it a lot? Is sort of more than half your group acting with fixed points? I don't have the right formulation of that problem or an idea how to solve it, but maybe someone in this room does. Yes, it does. That much I do know. Okay, so for the remainder of the talk, I want to prove some results. So here's the theme, that there's kind of this is sort of enough dynamical structure to get a relationship between kind of the dynamics of an action various dynamical features correspond to various structural features, like how leaves of the foliation meet or fit together. And sometimes actually this also plays into the structure of the group itself. So let me announce some hard theorems and then prove some easy ones. Okay, so here's some result along these lines. These are all in progress in a paper that's written but not in the kind of shape anyone should read yet. Joint with Thomas Barthelm again and Christian Bonatti. Okay. So here are some things that you can say. For any Anosov-like group action, so that'll be my standing assumption. G has an Anosov-like group action on a bifoliated plane. If this bifoliated plane is neither trivial nor skew, okay, so I eliminate sort of the two previously well-studied easy cases. Then, no matter what this was, point stabilizers are virtually cyclic. Okay. So some structure feature of my plane gives rise to some, I guess I'd say that's like dynamic / group theoretic structure of the action. You can make silly counterexamples in the trivial and skew case. Maybe here's another nice result. If G has no Z cross Z subgroups, many examples exist, then automatically the action satisfies this transitivity property. Yeah?
Yeah, if the position is either trivial or skew,
yeah.
Does it force that I should have a singularity?
Does it force the?
I mean, so like the Anosov flow.
Mm-hmm.
I mean, if I do not have some skew or, I mean, the R-cover case, I mean, so I'm saying, does it force that I should have a singularity?
No, yeah, so typical, I guess, Anosov flows have, but not, so pseudo-Anosov is what this undefined thing that says singularity. No, but many Anosov flows have this branching behavior of leaves, non-have sort of leaf space, but no singularities. So, and that's typical. There's tons of examples. Yeah. Other questions while I'm checking how much time left? Okay. So if you're a flows expert, this is somehow about how basic sets can be separated by tori or something like this. But you can prove this just out of these axioms using with a ton of work. Okay. So somehow a group theoretic feature gives you a dynamical feature. Okay, and what's on third? I made a list of sort of fun, easy to state things here. Well, maybe I should just say that sort of using some of this technology, T really does mean that the action is topologically transitive. Meaning that there exists a dense orbit. Okay, so this calling this axiom transitivity is not cheating at all. Okay. So this is the kind of things that you can prove, and the hope is that we can do a lot more of this, both sort of recovering things that are known in the special case of actions on bifoliated planes for Anosov flows, but then maybe some new things that are not. Okay. So those are all hard to prove. You have to write a whole paper. But let me prove some easy things just so you get a sense of how these kind of arguments start to get going. And maybe what I want to discuss is sort of this essential architectural feature of non-trivial planes where you have leaves that like don't meet but almost do. I'll organize this last 10 minutes around the idea of distinguishing trivial from non-trivial planes. You know how you like teach measure theory and that's hard, so you start with like what is measure zero versus not? Yeah, so we should go with like what is trivial versus not. So here's a essential architectural feature of planes that are not trivial. There are some leaves that don't meet each other but almost do. So here's the definition. This follows Fenley, I'll credit both Barbeau and Fenley because they're working around the same time and eventually start collaborating. Two leaves, let's say L plus and F plus and L minus and F minus, are said to make a perfect fit, okay, if they don't meet, okay, but this kind of picture happens. Okay, there exist little leaf segments. Okay, so here's L plus, here's L minus. There's a T minus little leaf segment in the other foliation based on L plus, and a T plus based at L minus. On L minus and plus, okay. So that any leaf that intersects T minus also intersects L minus, okay. And same with that, T plus L plus. So that any leaf meeting T plus or minus also meets L plus or minus with the same sign. Okay. So it's exactly this picture, or what you're seeing sort of at the corner there. Okay. All right. Okay. So here's a nice lemma that gets you going. As soon as you have these, you can sort of start concluding about some interesting dynamics plus structure. All right. I need space. Let's do this here. So I think I have just enough time to state and prove a little lemma about how we're doing this. Perfect. All right. Okay. So so I have, my axioms say I have some fixed leaves everywhere. Suppose I have an element that fixes a leaf that makes a perfect fit. Mm-hmm. So suppose G fixes a leaf that makes a perfect fit. So this is any element of my group with an Anosov-like action. And L plus makes a perfect fit with some L minus. Okay. I was using colors. Let's try and keep that up. Okay, so that hole is the edge of the universe. These do not meet. Okay, then here's the conclusion. Okay, well, right away from the axioms, I don't have to prove anything here. I guess I can stick it in the statement. There is a fixed point on this leaf. All right. Okay. That's not something that's one of my axioms. Okay, here's something that you have to actually prove. There, G fixes the leaf making a perfect fit with the fixed leaf. Okay, so it has a fixed point on this leaf as well. So. Okay. And the opposite foliation leaves through X and Y. All make a perfect fit. Okay. And my last piece of conclusion, other leaves through X and Y make a perfect fit. Okay. So out of a tiny bit of information about my plane, I have a leaf that's fixed and I have some other leaf that almost meets it. I get both the dynamical conclusion about something that happens somewhere else, okay, and a structural conclusion about something that happens in my plane somewhere else. And this kind of stuff that lets you bootstrap a little bit of information to something global. How do you prove something like this? We can just do it. So here's a proof sketch. Okay, so this part, is just an axiom. So there. How do I show that this is fixed? I guess I should say like up to passing to g squared, so that you're allowed to reverse orientation in theory. I didn't exclude that, so you could have swapped this. But g squared will fix these two ends, so that's really what I should say. So pass to a power if you need to, so you don't reverse the orientation of this leaf. And from the definition of perfect fit, you can think of L minus as a limit of any sequence of leaves that sort of exits every end and passes through L plus. Okay, so the first point, L minus is a limit of the set of leaves. I need another, maybe just L, so that L in F minus, so that L cap L plus not empty. And this set is invariant by g squared, so L minus should be also. You want to worry a little bit if in this branching kind of picture, the limit of this is multiple leaves, but this is going to be the one that sort of is closest to L plus, and you make a little argument. It's no problem. Okay, so that shows this part. There exists a fixed y. That's just axiom 1 again. And why do these? So I can look at the leaves through here. They're both fixed by g. Why do they have to make a perfect fit? They can't intersect. If these intersected, this is fixed by g squared because it passes through this fixed point. This is also fixed. So their unique point of intersection would also be fixed. And that's bad. That contradicts this global expansion contraction coming from axiom 1. I can't have two fixed points on the same leaf because I'm supposed to go towards one. So they can't meet. Okay. I'll sketch without writing. So now we have to say that they almost meet, right? As opposed to, there's a bunch of stuff in the middle here. So why do they almost meet? Why do they make a perfect fit? The thing to look at is take some big long leaf segment here, okay, and a family of leaves. So if I go close enough out to this pink one in the picture, and the definition of perfect fit says that some family of leaves of my pink foliation, I guess this is F minus, passing through this little transverse segment, will meet this leaf here. So this picture is not a lie. And a little product folded rectangle there. Okay, so draw this picture, and then let's assume up to switching with G inverse that my dynamics is going like this. I'm contracting in this direction, expanding in this direction. If I iterate this picture under G, if I iterate a ton, right, this part will shrink, And these will be carried along to a family of leaves. I can get as close as I want to this leaf through X that I'm trying to show makes a perfect fit. So I iterate this picture under G, and I get something that's this very short segment and a bunch of leaves very close. And this leaf is also fixed by G, so they need to continue to intersect it. Okay. And if I do this, forever, you show that if I take a little transversal here, any family of leaves passing through here, through this transverse segment, has to meet this leaf in question, right, which is half the definition of perfect fit. But my picture is symmetric, so you can do this in the other direction. Okay. So without writing, just drawing the picture, that's the conclusion here. I wanted to prove another little thing using this, but I feel I'm out of time, so I'll just state it as an exercise if you want to play with this and get a sense of how these things are used. Okay, so here's question? No, okay. So here's a fun concluding exercise, okay, which is the advertised characterization of trivial planes. Here's another little lemma. Again, this is originally, I think, appears in a paper of Sergio Fenley for Anosov flows, but you can prove it right out of the axioms for Anosov-like group actions. Okay. So if I have an Anosov-like group action on a bifoliated plane, and in the plane locally you see a feature that looks like this. I have a leaf segment of one foliation, and through this I see two others. All right. And I see, bounded by these two leaves, I see a product foliated region that goes on forever. So in a one-directional infinite strip, my foliation looks trivial. So this has to really go on forever. If this occurs, okay, then P is trivial. And of course, G is then an affine group by exercise number 1. Okay. So I don't have time to prove this one. You need to use this lemma at some point. I think this is a nice another further illustration of how somehow kind of local behavior plus some interesting bit of dynamics gives you something global. This is the kind of theory you can build up bit by bit to get a real structure theory of what this looks like. Oh, I should mention that there's kind of a converse to this lemma also. If you have some element that fixes more than one point, then actually these points are connected by a network of leaves that make perfect fits one with the other. Okay? So there's a lot of rich stuff here. I wish I had all day, but I'm out of time, so we'll end it there. Thanks very much.
Questions?
For the extended skew plane, do you have examples which are non-trivial central, things apart from non-trivial central extensions of surface groups?
Yes. Many. So you can make sort of like garbage examples by taking things that are not like in discrete. So actually, wait. Let me clarify your questions. Are you thinking about extended convergence groups, or are you asking about? Yeah. Okay. So even
your axioms.
Yeah. So satisfying the axioms. Actually, let me answer both your question and things. Satisfying the axioms, you can make kind of garbage examples by taking any subgroup of PSL2R with no parabolics, like indiscrete terrible, and lifting this. Okay. Looking very different from that, you can take the fundamental group of any manifold that supports what's called an R-covered Anosov flow, among which you have hyperbolic 3 manifolds, you have all kinds of stuff, and you get such an action, but we don't really know. I mean, it's hard to say concretely what these look like write down generators. Like, that's hard. Yeah.
Okay, thanks.
Any other question for Katie?
So is there an example where G contains Z cross Z, but property T does not imply that topological transitivity?
Where, no. So this oh, sorry. If T implies transitivity always. Yeah. I don't know if I may have written that down in a confusing way.
I think your statement was that T is equivalent to transitivity.
Yes.
So
Yeah.
Are you asking?
Yeah. So I guess and that, but the other thing only goes one way. No Z cross Z implies transitive, but there's transitive examples that have Z cross Zs. Maybe that was your question.
Yeah, I think that was the
I
question.
missed it somehow. Yeah.
All right. If there are no further questions, then let's thank Katie again.